Okay, so now we're getting into what we call muscle responses. After we've gone through the whole anatomy of the muscle cell, and then contraction phase and relaxation phase, we're going to see how individual fibers or maybe a whole muscle might respond to all that or the actions that it might take. So the first thing we discuss is called a twitch. So a twitch is you can read there response of a muscle fiber to a stimulus. So what happens to a muscle fiber after the acetylcholine is released at the axon, goes across the synaptic cleft, and we have that whole wave of excitation that leads to a contraction. Um, so this is basically taking all of that and recording it graphically, and you're going to see that graph here in a minute. It is a period of contraction and relaxation, so we're seeing the whole process on this twitch. We record it on something called a myogram, and that's going to give us something called a myograph, basically a graph of the line rising and falling as we're seeing a muscle cell contract. There's a few different parts of the twitch. First one is called the latent period. The latent period is just a delay. So when the stimulus occurs or the acetylcholine hits the motor end plate, there is a tiny itty bit of a delay before contraction starts to happen. So that's the latent period. We then have the contraction phase where, if we're looking at it on a graph, the line's going to go up, and then the relaxation phase where the line's going to go down. Okay. Um, this is the whole part of the twitch, and you're going to see again, like I said, here in just a moment. Um, we talked about a motor unit. A motor unit is a neuron plus all of the fibers it connects to. So all the fibers that are connected to each motor unit will all have the same twitch pattern. And we talked about how they'll all contract simultaneously. However, and it's important to note that it's not the whole muscle. The whole muscle will not have the same exact twitch. It'll have a similar pattern, but if we were to look at it at the millisecond level, it would not be exactly the same. Um, Sometimes twitches are affected due to injury. So if the fibers are stretched too far, think of like hyperextending a joint or something. The force of a twitch is going to decrease. That's because not all cross bridges are going to be able to attach. Why is that? Well, it's because the actin has been pulled a little bit too far apart. And when the actin's pulled a little bit too far apart, not all those cross bridges are able to make that connection. Sometimes muscles can be compressed, although it's not as um, common of an injury, but if they are compressed, sometimes that affects how a twitch might occur. Like I said a minute ago, a whole muscle has a ton of motor units associated with it. So when we do, so let's say you're doing curls in the weight room, if I were going to graph that, it would look like an individual muscle fiber twitch. But again, if we went to the millisecond level and we're looking at it microscopically, not all of those fibers will be exactly the same. Um, Here we go. So let's talk about force, how we need to change it for different activities. That's going to be more appropriate on the next slide. But the force that we need is going to reflect what? Well, how often a muscle fiber is stimulated. This is something called summation, which we're not really going to go over in this unit. But summation is like if I can get twitches happening over and over and over and over again in a fast pattern, it could cause a stronger contraction. And then how many fibers are taking place. Okay, so I've discussed this a little bit, but that's going to, again, be more appropriate on our next slide. This is what a twitch looks like. You see the stimulus over there at the 0 second line. Then we have the latent period, that brief delay. As the graph is going up, you have contraction. As the graph is going down, we have relaxation. Here's what I talked about a minute ago. We don't necessarily cover tetanus and summation and stuff like that, but a single twitch of a muscle fiber. But these arrows all represent stimulus coming from a neuron. So sometimes we will combine these stimuli from the neuron to give us a longer contraction or to repeat a contraction over and over and over again. And if those stimuli get close enough together, it's going to seem like it's just one long contraction. But again, We don't need to worry too much about that right now. From there, we go to a couple of interesting concepts. First one we have is called the all or none principle. The all or none principle says this: when a muscle fiber is contracted, it will contract all the way or it will not contract at all. So, what does that mean? I can't just tell my muscle fibers, you just contract a little bit this time, and then the next time, give me all your force. It's not really how it works. Our muscle fibers go 100%, all effort, all the time, or not at all. Now, you may be saying, wait a second, you just said something about holding a styrofoam cup versus squeezing a ball or something like that. Well, that's going to involve multiple motor units. So when we are talking about this, just think about I will only get a certain amount of motor units for each activity, which we'll cover in just a second. And also that second bullet point says warm muscles are able to contract more strongly than a cold fiber. So if you look at the definition, it says muscle fibers contract with all the force possible or not at all. It should say at that time. What that means is sometimes they're only able to do a certain amount of work. A warmer muscle can do more work because, well, it's stretched out, it's warmed up, it's got more blood flow into it, so on and so forth, than a cold fiber would. This deals a lot with all or none principle. It's called recruitment. If you think of recruitment for like an athletic team, they're trying to get more athletes to be a part of their team. So recruitment of motor units is I'm trying to recruit more motor units to do more work. So this goes back to if I'm drinking a cup of coffee in a styrofoam cup, I don't want to use all of the motor units associated with my forearms, or I would squeeze that cup and spill coffee all over myself. So I'll just use the motor units that I need in order to do that task. And again, that relates back to the all or none principle because the new units that I'm using, even though it may just be a few, are doing all of their force at that time. Some muscles have very few motor units associated with them, so they'll have very precise movements. So, for example, like in the eye, there's very few motor units, so you can do a little bit quicker activities, a little bit more precise movements. Think of texting with your fingers, have very precise movements because there's not a lot of muscle fibers, motor units associated with those. Whereas, like the muscles in your back, the muscles in your legs, your quadriceps, your hamstrings, those contain tons of motor units. And each of those motor units is connected to more fibers. So, therefore, the movements that you do with those are not going to be as quick or precise. So all of this is basically going over everything I just said there. It says the whole muscle is consisted of many motor units controlled by many neurons. So basically what our body will do as we recruit is we will recruit the smaller ones first. A smaller motor unit would be a neuron connected to just a few muscle fibers. And then the more force we need, we'll recruit those larger ones and larger ones and larger ones. So you'll recruit all of those muscle fibers when you're doing, say, a squat in the weight room. So there you go, recruitment. It's going to increase the number of activated motor units. It says as stimulation continues, recruitment continues until all motor units are activated. So that's what I just mentioned with doing your squats. Our next muscular response is called TREPPE, T-R-E-P-P-E, or the staircase phenomenon. It says a gradual increase in the strength of a contraction. So if I continue to twitch, go through twitch patterns, every time I twitch, the more warmed up my muscles get, the stronger the contraction becomes. And it's just this tiny itty bitty steps or staircase phenomenon as I go up and up. Okay, it says muscles contract harder after they've been contracted a few times. If you've ever played a sport, you know that your coach makes you warm up and stretch before you do anything 100%. It goes exactly back to this phenomenon, the staircase phenomenon, or TREPPE. And it's physiological. It's physiological, meaning that You may think you can just hop out of the stands and go out and perform at your highest level. It is impossible to do that. You may think you can just hop on a bench and do um, hit your max bench press without doing a few warm up sets. It is impossible. You have to warm those muscles up and allow them to go through that gradual step like increase with each twitch before you can get as much force as you can generate. But eventually, you reach this thing called muscle fatigue. If you continue to twitch and twitch and twitch and twitch, even after you've reached that highest level, eventually you're just going to get tired. Your muscle cells get tired. You see, it says it lessens in excitability. And even if you're giving it a bunch of stimulus, meaning your neurons are trying to fire it, well, they're just tired. They're worn out, and they're going to reach that muscle fatigue. This is what the trepe looks like, the staircase phenomenon. You see that with each impulse, the twitch gets a little bit higher until you reach that max force or max tension there. That's trepe or the staircase phenomenon. And then finally, you get to this video, which is on your slideshow. So I'm going to have you watch that on your own. But that is our muscular responses to different stimuli and how we look at it.